eine Vorlesung sozusagen, eine geteilte Vorlesung, shared. Insofern, dass es typischerweise eine Bachelor-Vorlesung in den mathematischen Studiengängen ist und dass es aber auch eine Wahlpflichtveranstaltung im Computational Engineering ist. Ich sehe schon die Hände hochgehen. Ich gehe mal davon aus, dass es hier einige Studenten gibt, die eine deutsche Vorlesung nicht verstehen. So I understand that some of the students from computational engineering would like to have the lecture in English. Okay, so that is the rule, that we are doing that as long as you are here, as long as you require that. I know that the German students, they do not like it really, but on the one hand side, it's a good exercise for them, also to learn the English nomenclature, and on the other hand, as a small balance of this, the transparencies will be in German. So the lecture, as long as we have the computational engineering students not able to speak German, will be in English. Okay, so let me explain a little bit about the organization and about the prerequisites you have to be successful here. So these are the dates. In principle, it's very difficult to change the dates, so maybe we just do not touch this. I hope everybody, and I assume everybody who is here is able to cope with those dates, both for the lectures and for the exercise group. So lectures on Tuesday and Friday, and the exercise group on Tuesday in the morning. Okay, so in everything, all the material, all the exchange with you is via StudOn. You see here the password you need for that. You will in particular can download a version of the transparencies which I'm using from there. So everything which is on transparency, it's not necessary to make notes on that. But from time to time, I will say something which is not on the transparencies. And it's not as 99% of all the students think everything what is on the blackboard and what's on the transparencies of important. Everything what is said in addition is not important. Quite often I say quite important things which are not on the transparencies. But you will see that. Okay, so but everything what's on the transparencies, and that is basically most of the material you can download. At the end, we will have a written exam of 90 minutes, and that is, I don't know what the translation is, that is the Prüfungsleistung, and the Studienleistung is to take part successfully in the exercises. That means you get homeworks, you get assignments, and on weekly basis, and you have to work these out. They are theoretical homeworks where you have to, in the end, achieve 50% of the credits, and there are practical homeworks, meaning you should write programs which reflect the methods we are discussing, and we decided that as a basis for this programming work, we've taken MATLAB, because we could also change this, but we thought that is maybe the most accessible way also for mathematics students who maybe have no clear C or C++ education. So C or C++ would be the alternative, no other alternatives. Everything else doesn't make sense. So all these fancy things you might know from computer science, we certainly will not use Python or whatsoever. Okay. Maybe we first, to get a sort of an overview, let me first check. Who is from computational engineering? 5, 6, 7, 8. So you all are capable with MATLAB? No problem? No? But MATLAB is very easy to learn. The mathematics students, are the rest, I would say? Or is there somebody else who's not belongs to one of these two groups? Let me check with the mathematics students. Who of the mathematics students is not a good C or C++ programmer? So you're not doing computer science as a second subject or something like that. Okay, so that's what we were afraid of, and that was the idea of taking MATLAB. So I think we should stick to MATLAB. The point with MATLAB, as you know, MATLAB is not really a programming language. MATLAB is a toolbox. And of course you can deal with MATLAB as you would have C or even Fortran or whatsoever, but that's not the issue. There, of course, in the end, we will also write efficient programs. So in the exercises, there will be some hints given, and maybe as a sort of incentive for the computation engineering students, it's now very fashionable also to give bonus credits. And everything which is concerned with doing the more practical things, the programs, dealing with our computer rooms and so on, you have to contact Tobias Elbinger. What did I forget?
I think that's almost everything we said. So once a week you will find up from the next week on a home worksheet on our stood-on homepage for this course, and you will find it our course either on the path from the Bachelor Mathematics. It's called as the lecture as well, Einführung in die Numerik, Partieller Differentialgleichungen, or you will find it on this URL. Here important is this number. Maybe you'll write it down.
Maybe one practical thing: has everybody access to a PC pool where MATLAB is installed, or has it at his own notebook, laptop, whatsoever? So the mathematics students should have an access automatically, more access. And about the computation engineering students, where do you work usually?
In informatics, actually we have access
to MATLAB. Okay, so
MATLAB Octave, and we have
yeah, okay. In principle, but das ist, wollen Sie was zu dieser ganzen Octave, Scilab und so weiter Geschichte sagen?
The Octave functions for plotting are not as good as the MATLAB functions, and also there are some preconditions missing in Octave. So if you can use MATLAB, you should use MATLAB.
It's basically the question whether you want to work at home or you want to work here, or if you don't have an own license on your PC.
in case you don't have an own license for MATLAB, so is there a pool in a temporary license that is provided by university, or we have to figure that out?
When you work in the university pools, if you work at the PCs here, you have it available, but you cannot transfer it to your own PC. But there should be students' licenses for, I don't know, 60 euros or whatever.
I think they were free a few years ago. If you go to the page of the RR setting, but you can try to find it, but actually it's not necessary. As well, you could also log on via SSH on the subgroup and use MATLAB with -cx. So if you want to work from home.
Okay. So if you have any organizatory questions or any kind of questions, please contact these two. You can find them on our webpage, and their email address is now as the standard university email address. Oh, we have it also here. Yeah, I see it here directly. This is still the old version. There should be also a more newer version, probably Raphael Schulz at fau.de and Tobias.Elbinger, I guess, at fau.de, as we have now this unified addresses, just FAU. Okay, anyway. Okay, so maybe I tell you a little bit what this lecture is about and what the requisites are. So as I said already, I basically will use transparencies, not for everything. Ich glaube, wir haben das organisatorisch besprochen. Proofs I will then do also at the blackboard. So this is about numerical methods to solve. Solving means to approximate partial differential equations. Of course, now the question is which kinds of prerequisites you need. We discussed already that we do not want to do theory alone. We certainly want to do theory. That is not a course in finite element program. That is not a course in whatever simulation whatsoever. That's a course in mathematics. That is the major point. So we will develop the schemes, and in particular we will analyze the schemes. But of course only doing so, that would be just swimming without water. But of course we also need the practical experience how these things work, and for that we need their own implementations. Of course all kinds of implementations exist already of these simple things. We need their own implementations to experiment with them, to get a hands-on, to get some feeling how the things work. So what about the prerequisites? First of all, it's not as bad as you might fear. You should have a good working knowledge of the basic mathematics. For the mathematics students, that means of the linear algebra and the analysis, in particular the multidimensional analysis. These things I will use more or less without mentioning. Of course, any case you have questions, you can ask them. But of course, I cannot repeat the analysis in total, and I cannot repeat the linear algebra in total. For engineering students, that would mean mathematics in the range of the mathematics which is taught, say, in the mathematics for engineers 1 to 3, something like that. Then, do I need basic numerical methods? Do I need what is called Einführung in die numerische Mathematik or Numerik für Ingenieure? Of course, it's helpful if you've done this already, but it's not indispensable. If you at the bottom of everything, as you will see, we will solve linear sets of linear equations, pretty large sets of linear equations. So if you know already something about that, which goes beyond the Gaussian elimination method, that is certainly helpful. But and I know I'm not afraid about the students from computation engineering, because I know computation engineering, the conjugate gradient method is analyzed 20 times, I think. So they know this already, maybe the mathematics students not so strongly, but to get an overview from the mathematics students, who has attended Einführung in die numerische Mathematik? So basically all, or who has not? From the mathematics students, or all? You're a mathematics student, but you haven't had this class. It's not so decisive. It's a little bit helpful, because then you know already what conjugate gradients are. That would be helpful. But then we can control a little bit how much time we use for that. Okay. What is the next question is, what do I have to know about PDEs? Now I could make my life easy. I could say, okay, you have to know the analysis of PDEs. Then you all go home, and I don't have to do anything for the rest of the semester. I will not do it as easy for me and say, okay, what you have to know, I will integrate into my lectures. So it's not necessary that you have already had a course on PDEs. Of course, again, it's very helpful if you have had either something what is called elementare partielle Differentialgleichungen or partielle Differentialgleichung, but at least the second one is certainly not necessary. That does not mean that we do not need theory of PDEs. PDE is the abbreviation, maybe I haven't mentioned this, abbreviation of partial differential equation. But we will develop it, what we need. What is more important, what would be more helpful, but it's also not really a prerequisite, is if you know already something about functional analysis. And there is an introductory course in Bachelor for the mathematics students, and I think also for the engineering students there is a course of this name. So whom of you has already had a course with functional analysis in the title? Oh, that's quite a bit, and that is very good, because that would be really helpful in... So the thinking what we are doing is, say, functional analysis based, linear functional analysis based. Okay, so, but you will see what you maybe still need or not. Now the basis of, let me go first to this page. So the basis of these lectures is my book with Lutz Angermann. It exists both in German and in English, and there should be a reasonable amount of copies available at the library, so you can work with both. They are not 100% identical. The German edition still has a lot of misprints, but there is a errata list. The English version is a little bit enlarged, but this enlargement does hardly play a role for this semester. It is more important for the next semester. There are a lot of books on numerics of PDEs. There are some further mentioned, which I, to some extent, also recommend. If I have some time in adding some additional material, we will see, then I will basically do this on the basis of this book of Bräs, which also, here, this is the German edition, Finite Elemente, but there's also an English edition, Finite Elements, available. So all the books which I'm using are both available in German and in English. So you can make your choice. Okay. So let me just describe a little bit what we are talking about. So what we want to do is we want to deal with partial differential equations. More precisely, with boundary value problems for partial differential equations. Typically, this type of equations cannot be solved explicitly in terms of a formula, as you might know it for some simple linear ordinary differential equations, or even not so simple linear ordinary differential equation systems. There's a certain solution theory which you have some hope to build up a closed form solution. In partial differential equations, usually this is not the case. Of course, some exist. So we need approximations. Approximation is done by discretization. Discretization means that the infinite dimensional problem, which just comes to existence because we have infinitely many points in a 1, 2, 3 n-dimensional domain where the equation lives, has to be discretized. And so this infinite dimensional problem becomes a finite dimensional problem, as many dimensions as we have degrees of freedom than in our discretization. This is discretization. So we talk about different types of discretizations of very specific types of PDEs. That meaning, as is written here, approximation of the infinite dimensional problem by a finite dimensional problem. So we end up in the end by a large linear a large set of linear or nonlinear set of equations. Where then, of course, it's helpful to say I know basic numerics, and I know how to solve a large set of linear equations, or even to say I know how to solve a large set of nonlinear equations. By the way, how you would do that to solve a large set of nonlinear equation? What would be the key word? Just one name. Newton. Newton's method is the working horse, and all kinds of variants of it. Okay. Which again leads then sequentially to the solution of linear sets of linear equations. So on the very basic level, there are very large sets of linear equations. Say, starting from 10 to the 4 unknowns to 10 to the 6, or 10 to the 8, or maybe also 10 to the 9. That's maybe the limit one can go to at the moment. And that one can go up to this limit has to do with very specific structures of the equations which come out, as we will see. So we will learn about different approaches to do that. We'll start with the finite difference method. Who has heard already of this? Okay, these are basically more or less the CE students. In how many dimensions? 1, 2, 3? 3. Huh? Okay. Okay, so we will deal with this a little bit. It's a very easy to comprehend method, but method with extreme limitations, as we will see. And the method which in the last, say, 30, 40 years was the method of choice, the so-called finite element method, which abandons a lot of these difficulties of the finite difference method. It's not so easily to comprehend, so we will get step by step into that. In principle, we would need a little bit of function analysis, but we do this very, very inductively. And in the end, of course, what we want to do is we do not want to go just the way to set up in the end the discrete problem, but we want to analyze what we are doing. So we want to understand what this discrete problem has to do with the unknown continuous solution of the PDE problem. That is the mathematics part, so that words like convergence, order of convergence play a role. This will be a major aspect in the course. That is what we have here. Of course, then we also want to solve these equations, so we need specific method, and of course we want to implement it. That we have discussed already several times. Okay, so now when you have dealt already with ordinary differential equations, then you have experienced that there's a sort of a general theory for ordinary differential equations. There's Picard-Lindelöf, or whatever the basis for you is, that you have a certain unified existence theory and so on. For PDEs, this is not the case. Each PDE sort of stands for its own because it reflects different physical problems. And the point, what we certainly will not be able here is to integrate a whole analysis of PDEs or even of certain classes of PDEs. But what I would like to achieve is that in the end, or very soon, you are able to read a PDE. That means to look at a PDE and say, this term means this, and this term means this. So this goes a little bit in the other direction. This goes in the direction of mathematical modeling. But at least introductory, we will do this a little bit. We try to understand how PDEs appear basically in physical and technical applications. They are the same sort of similar application from the biological and the chemistry side. There are even applications from finances. So this is really spreading. Okay, a real analysis course would deal with the existence and uniqueness of solutions of these infinite dimensional problems and their continuous dependence on the data and whatsoever. And I will only deal with that, as I said, as far as I needed to develop the discretization methods. This we looked already. So this is a sort of an overview what we are doing. So I said already we start with the finite difference method for a very specific problem, which is called the Poisson equation. I will introduce it in a second. Then we do some basic theory, and we see the limitations of the finite difference method. Then we switch to the finite element method in its most simple situation for the Poisson equation as the most simple equation. And when we have understood everything there, then we do the same thing in general, what is then called linear elliptic boundary value problem of second order. All these words I'm going to explain in a second. And then finally we have to deal how to solve the linear sets of equations, sets of linear equations. So we have to deal with iteration methods. That depends a little bit what you know already. How much time we have to spend there, and that's basically, is it For this semester, maybe if there's still some time, I can go to other discretization methods which came up in the last decades, which are maybe superior in several cases to the classical finite element methods. These are variants of finite volume methods. These methods called mixed finite element methods, or a very modern version is called discontinuous Galerkin method. This depends a little bit on the time. What is common for all the problems we are looking at in this semester is that we are only looking here at stationary problems. What that really means, I will explain also in a second. It means that we are looking at problems which have where the quantities which are unknown and which are of interest vary in space, but they do not vary in time. And the variation in time, the time-dependent problems, that is something which will then be the subject of the next semester. Okay, let's start with some. So I will start a little bit to introduce now in this preliminary, in this zero section, what kinds of, how the equations look like. We will look at eventually, and then I will also show you some examples. I will do a little bit of CFD, colored fluid dynamics. So I show you a few colored pictures and movies. That's the only occasion where I do that. All the rest we will just do mathematics. Okay, what is a PDE? What is a partial differential equation, PDE, or German abbreviation PDG? One can say it very simple. It's an equation for an unknown function. The function usually in mathematical terms is denoted by u. In applications, the letters vary a little bit depending what you want to describe, but we will usually call the unknown u. So you know already where the unknown is, just look for the u. This u is defined on some set, usually called omega, in a typically multidimensional space. The dimension is here in the following denoted with d. So typically d is larger or equal to 2. So the normal situations would be if you think at real space, d would be 1, 2, and 3. That's it. But there are also applications from finance where d can be 20 or 40 or whatsoever. Okay, so we have a function in several variables. This is unknown, and what we know is an equation which in some way connects this function and partial derivatives of this function. That is a PDE. In this generality, that doesn't make any sense. But I give you first an example, maybe the most important equation, and we will deal a lot with this equation. It's the Laplace equation in this upper version, or called Poisson equation in this lower version. So what does that mean? This symbol nabla we will use quite often in the following, and this is an abbreviation for this quantity. So I take the second partial differential derivatives for each variable. I have d variables, and I sum these up. So in one dimension, this is just uxx, in two dimensions uxx plus uyy, and so on. And the requirement is, in the Laplace equation, that nabla of u equals 0, or in the Poisson equation, nabla of u equals a given quantity f. And you see here, for some reasons which will become later, I prefer, at least in this case, not to write nabla of u, but minus nabla of u. Of course, there's no difference. I could put the minus sign back and forth on the right-hand side, but we will see later on the real natural operator is not nabla, it's not a Laplacian, as we call this operator also the Laplacian, the Laplace operator. It's not the Laplacian, but minus the Laplacian. Okay, so we have an unknown function u in d variables. We have maybe given a right-hand side. F in d variables we're looking for is a function. And now we see, before going on, we see several things. This is an easy problem. Why is it easy? Because it's linear. And linear problems, as you have now experienced with linear algebra and nonlinear analysis, the linear problems typically are the easier ones. Why is this a linear problem? Because we have the similar sort of property, as you know, from matrix operators. Namely, if I have two solutions and add them up, they become a solution, or they add up to a solution for the sum of the right-hand sides in the second version, and the same thing if I multiply with a scalar number. That is one thing, and the other thing is something is missing here. Why is something missing? What would I expect for a mathematical problem? I would expect that a solution exists and that a solution is unique. If it does not exist, I have required for something which doesn't make sense. If the solution is not unique, that means I have not put enough information in my model. What is the problem here with this equation? Yeah, we don't know what boundary conditions are, but what is the consequence of that?
We're not sure whether there exists a solution.
There exists a solution. Let's look at the Laplace equation. Does there a solution exist? Give me a solution for the Laplace equation. Yes, another one?
1.
Okay, another one? Okay, you got it. Okay, you can also go a little bit higher. You see, you only have derivatives. And of course, therefore, you cannot see constants. You cannot even see first derivatives. So something is missing in this problem. Okay. So we'll come to that later. So now we will see how we can, by some principles of continuum mechanics, we finally end up with such PDEs. This problem, what was already mentioned, the so-called Randwerte, boundary values, we will discuss later. And I hope most of you know this already, but I repeat it a little bit. You know that most of continuum mechanics modeling, so to speak, most of what an engineer does, an engineer only lives, a real engineer, lives at the continuum mechanical scale. And what does that mean? That means there are basically three quantities which are preserved. This is energy, this is mass, and this is momentum. So we have to see what plays a role for our problem, and we have to prescribe this preservation, and in the end come up with an equation, a PDE for the quantity we are looking for. So this I will demonstrate you a little bit at an example here. So this is one way to come. There's also another way to come from extremal principles of energies. So let's look at, and of course, in this process of description, not only quantities appear, but also rates. And rates are derivatives. So we do not end up with algebraic equations, we end up with equations with derivatives, either ODEs, if you only have one independent variable, or ODEs, ordinary differential equations, or PDEs with several independent variables. Okay, let's do this example. We have an unknown function u. That's a scalar function, an extensive function with a certain unit a. We can almost be more precisely and say this is some substance dissolved in the fluid. So we measure the a, either we measure it as in kilograms, as a mass, or maybe better in moles. Doesn't matter so much. Then we have the volumetric density of this quantity. So this is now something like a by volume. And the principle we want now to apply is mass conservation. So in this case, in the case of mass conservation, as I said already, S of u is a concentration. It's mass per volume. And the way to derive the corresponding PDEs is to say I have a certain domain. We call this a domain then, this multidimensional basic space, omega. We will be more precise in a second what a domain really mathematical means. At the moment it's just a subset. And we take any small subset omega tilde of that, a control volume one also says. We look at this arbitrary small or large volume, and we look at the mass which is in this volume. Okay, if S of u is a concentration, then the mass is the integral over S of u over this part. And if we look at the temporal variation, we look at the partial derivative with respect to time. That is the way I write partial derivatives, if I have to write them explicitly, with a delta t or delta x or delta xi or something like that. So that is the quantity that is the storage term, which maybe varies over time. But if we have conservation of mass, that means the only way that this term varies over time, there are two possible reasons for that, namely, what are possible reasons for this variation, for the fact that this term is non-zero? When can this be non-zero if mass is conserved?
Mass in, mass out. Domain.
Yeah, mass can flow in and out of the domain, and what else can happen?
There is no generation.
There can be a generation or a destruction of this quantity. That's all what is possible. Okay, if we have such an internal source, which is here denoted by the Q, so this is now a quantity A by volume by time. So it's a volumetric density. We get some contribution of this one. And finally, as already mentioned, there may be a flux of this quantity over the boundary delta omega tilde. So the boundary always I denote, think of the topological boundary at the moment, at least in the topological sense you should know this notation. We denote this flux by J. So J is something like mass per surface per time. That's the flux density. So this is a vectorial quantity. Till now we had scalar quantities, but that's the first time where a vectorial quantity, a vector field, appears. And each component says that is the mass which flows in this direction, in this specific coordinate direction, through a unit surface by a unit instance of time. So now let's write down what we have. So we have the temporal variation of the total mass, and it can only be caused by two reasons. The one reason is that there is this distributed source or sink. So if this is greater or equals to 0, it's a source. If it's less or equals to 0, it's a sink. That may also vary from point to point what it is. And again, we have to integrate here to come from the concentration to the masses here. So that is the distributed contribution. Quite often this is not dependent on, might depend on the solution. Quite often this does not depend on the solution. And there's the second quantity which describes the flux over the boundary. And therefore we need this mass flux field. And in addition we need the unit normal of this boundary. So the situation is as follows. We have in 2 dimensions, we have our domain. Let's say this is our domain. And if the domain is smooth enough, we will make this more precise what that means later on. This is our omega, this is our delta omega. And that means we can at each point of the boundary, or at almost each point of the boundary later on, we can define a vector field, which is a unit vector field. So the length of each of these nu of x is 1 in the Euclidean length. And it's an outer normal. That means a vector field pointing orthogonally outward of the domain. You know from linear algebra what means orthogonal, what means perpendicular. And here this is quite similar. Of course, it depends. It requires a certain regularity of the boundary of the domain. For example, if you know that the boundary, for example, is given as a surface of a function f equals 0, let's say, such that in the interior we have f less than 0, in the outer world we have greater than 0. And that's something we do not need globally. It's often quite impossible to do that globally, but we only need it very locally here. Then, of course, how can I then define the nu in this situation? What can I take as nu, as the unit outer normal in such a situation? What is the direction in which the f varies maximally? not quite. I want to have a unit normal divided by its length. So in this case, I could define here nu of x just as the gradient of f of x divided by the Euclidean length. The gradient, I use this notation here. I think it's also quite standard. And that means locally I have to be able to do something like that. To do what in this has if this f is say a k times differentiable function, one would call such a domain a CK domain, and on the other hand side one can go down up to Lipschitz functions, and this is the minimal requirement. What we use is that we have a Lipschitz domain in this sense, but I will define these things later on. So we have the outer normal, and then we have here a minus sign, so minus nu is the inner normal, and that means this is the quantity what flows into the domain. That is the if there's something to flow into, that gives a positive contribution, equally as a positive q gives a positive contribution. This is what balances these variations in the storage term here. That's the only reason for storage. Okay, now you know, hopefully all know the divergence theorem of Gauss. Okay, and this tells us, even you should just know it. I don't require that you give me a proof of it, but you just should know it. This tells us under certain conditions on this vector field, on the domain here, and so on, we do it only formally here, I can rewrite such a surface integral in terms of a volume integral over the divergence of the field. And that is the way I write the divergence, as gradient dot, because that's what it formally is. It's formally the scalar product, because only very formally the scalar product of the gradient and the vector field, because it's the sum over the derivatives, of the ith derivatives of the ith component. Okay, so we end up now with this, say, integral relation, and we have this integral relation for each of these arbitrary domains omega tilde. And again, now only formally, under certain regularity assumptions on these quantities, the only way that this equation holds is that this function here is 0. So that is now we get the transition from an integral relation for every possible control volume to a pointwise relation, which then looks like this here. And now we have here already a PDE. That is now our basic PDE here. This is still a time-dependent problem, so it's not. We will not deal with it in its full generality. So there's still a time derivative. Here we have spatial derivatives. Here we have, let's say, more of a given quantity, or at least something which has no derivatives. So now you see there's something missing. We have, how many unknowns do we have? Even if we say this nonlinearity S is given, or it's just factor times U in the most simple case, we have the unknown U, and we still do not know anything about this flux quantity J, but we only have one equation at the moment. There's so we need more equations. And these further equations, they come from, they are more phenomenologically based, or they can also be made more rigorous. That means we need constitutive laws which relate the fluxes to the extensive quantities. And that depends on what we are going, so we need some relation between the J and the U. And this gives us the further D equations which we need. Okay, so let's do this for this example we have in mind. So we have a container with a fluid in rest. We have some substance dissolved. U is the concentration of this substance. J is the flux of the substance. So make it a little bit more precise. You have a cup of coffee, and you have a spoon with sugar. You put the spoon into it. Now some quite complicated dissolution processes take place, which I'm not discussing, at least not now. And now then you have the sugar in your coffee. And then, what then? drink. And when you drink, then you will see, oh, the sugar is somewhere else. It's not where I want to have it. So we will do something different in addition, which we will discuss later on, that what you do in addition is taking a spoon and you stir it. That would be one version. The other version, if you're more patient, you just let your coffee stand there. You wait and wait and wait and wait. And then in the end, the sugar is equally distributed. Because there's a process going on which is called molecular diffusion, which in its consequence means that a substance is moving from points of high concentrations to points of low concentration. And the most simple, let's say that's an experimentally found law. It's called Fick's law. And in its most simple version, it says this flux, which is called now J1, because there's another part of the mass flux we have to take into account, as we already have heard, is proportional to the negative gradient of u. The gradient of u is the direction of steepest ascent, the direction where the function changes maximally. So minus the gradient is the direction where you go down maximally. And we have proportionality. That say we have here some parameter, some positive parameter, which is called the molecular diffusivity, and that is the most simple relation we get. Now we plug this in. That's one way to do that. We plug this in. We could do the same thing with temperature. That's the same thing. And then this equation is called the heat equation. The equation we now got is called the linear diffusion equation. And with temperature, we have this slight further thing to think about. In dealing with temperature, being interested in the variation of temperature, the conservation principle is energy, is inner energy. So we need first, on the one hand side, a law which relates the heat flux, which relates the energy flux to the variation of temperature. That is Fourier's law. And on the other hand, in the conservation equation, we have this S of u, which is actually the interior energy. We need a relation between the interior energy and the temperature. In the most simple situation, this is just a proportionality. So we are back to the same types of equations up to some factors. So I skip this maybe, and I come back to my diffusion equation. And that is what we did. We plugged this now in here, and now we see what we got. We have now really a partial differential equation. We have a time derivative here. We have a divergence of something. And this is very important also for all our derivations of methods, that this divergence is there. This having the PDE in divergence form, as it is called, just means there's a conservation principle behind it. We just not have written down something. Of course, with d variables, you can write down all kinds of equations. Whether they make sense is another question. Of course, there are also models coming from physics, coming from technical applications, coming from the sciences, which are not in divergence form. Don't misunderstand me. But we will concentrate very much on the divergence form. And in the divergence, we now have k times the gradient. The minus here is here taken out here. So what does that mean? That means is if you differentiate this out formally, if the k in the most simplest case is just a constant, you get again second derivatives. More precisely, you get the Laplacian here again. If the k is just a constant, what is given here is just k times the Laplacian of u. That is the heat equation, the diffusion equation. If the k itself is dependent of x, meaning that you have an inhomogeneous materials, your diffusivity varies from place to place, then if you differentiate this out formally, you see the derivatives go on the one hand side to the gradient of u. This gives rise to the second derivatives again. But you also get derivatives going to the k. And then you get first derivatives times first derivatives into the equation. And then on top of that, therefore this is here printed with a bold letter. A bold letter, as you see, I use here either for vectorial quantities or for tensorial quantities, also say it a little bit more simple for matrices here, for positive definite matrices. Having here a matrix means our constitutive law is a little bit more general. It does not say the flux is directly in the direction of the gradient, but there might be some variation. There might be some rotation going on. So in the most simple situation, so if you have an isotropic medium, that's how it is called, we have here, say, our gradient of u, and this here is then our j. In the anisotropic medium, what can happen is, it's the most simple situation, maybe some small rotation, and then this is your j. The point is, of course, you can imagine it doesn't make sense to say J is just a matrix, then K can be 0 and anything, then the whole term vanishes. So the prerequisite then is, and this is the situation we will deal with, is K is positive definite. K being positive definite means if I multiply, what does that mean? If I multiply gradient u by k and then compare in the scalar product with the gradient of u, I have a quantity which is greater than 0. What does that mean about the angles between k times gradient of u and gradient of u? If I have something, so if k is positive definite, what does that, then I have, of course, gradient of u, I write the scalar product with I say with parentheses like this. Then I have this sign here, that's the definition. And what does this mean about the angle between these two vectors? 360 degrees also positive. It would be bad if this would be 360 degrees, because it would mean it would turn everything upside down. Now it goes up the hill, not down the hill. Would be a bad thing. It would be anti-diffusion instead of diffusion. But you cannot tell me that you don't know how the Euclidean scalar product relates to angles between the vectors. You're not willing to tell me that, or are you? Was something with a cosine, wasn't it? Yeah, what does that mean? Cosine positive, what does that mean for the angle? Now we are back to school mathematics, fifth class or something like that. In which class my daughter is now? In the ninth class, I think they started doing this with a cosine. Now we are at the level of the 9th class in high school. Okay, so which angles does that mean? Positive cosine. To 90 degrees. So we are not allowed, so to speak, to miss this principal direction. We can deviate a bit, but we cannot turn it in the other direction. This is what it means. Okay. So that would be one of our basic equations here. But now we saw already, okay, maybe we are not as patient as we are now. We stir our coffee. That means we impose a flow in this fluid. There's a certain flow field that is here denoted by C. It's again a vector field. And what does this flow do? It produces forced convection, meaning it just takes the particles and carries it with them. The mass particles or the heat particles or whatsoever. That means we have additional part in the flow which is just U times C. It's exactly the given flow field times the concentration. And if we plug this in, the diffusion equation becomes the convection diffusion equation. That is, we have this additional term here. That means even if we now only look at the most simple case where the K is constant and also say the C is constant, that means we do not only have second order derivatives here in the equation, we also have first order derivatives here in the equation. And they describe, as you have seen, totally different physical processes. The one is a directed process, the convection. The other one is an undirected process. There's Brownian motion behind that. And this is reflected in a totally different mathematics. And of course, in totally different requirements for the discretization. So only alone in this extremely simple equation, we have now gathered together two quite different processes which have to be dealt with. And there's one thing which I have now missed on this transparency, and that is called the transport equation, or the linear transport equation. And that is the situation when I say, okay, I stir so violently that this little bit of diffusion doesn't matter. If there's additional diffusion, who cares? That means I go to the limit in my problem, I forget about the diffusion. What does that mean? I write down an equation of the type, I do this now formally, I forget about the k term, I set the k to 0, and I have here minus divergence of c times u. So I have only now first order derivatives here. Let's say a special situation. If the divergence of c is 0, that is a very special but quite often appearing situation for a flow. What does that mean? If I differentiate this out, then the term divergence of c times u vanishes, and what is left is only the term minus c. So here in the equations, here I've used maybe for the notations. Here, if I really do computations, and to deal with the Euclidean scalar product, I use parentheses, either the round ones or maybe even the kinky ones. But if I write down equations here, to reduce a little bit the notation, I just use this dot here for the Euclidean scalar product. So then the equation boils down to this one. So I have here one time derivative, and here I have my first order spatial derivatives. And we will not do anything about the numerics of this equation. In some sense, it's the most simple PDE which exists, but it's also in some sense a difficult one. But what we will look at is maybe a little bit the limit. What happens if these forces become important? Okay. So now, as I said already, these time-dependent problems, that's something I would like to treat in the next semester. Here in this semester, I want to restrict myself to the stationary situation. We can imagine the stationary situation as a process which is going on. So let's go back. Either this equation or this equation, your sources and your boundary conditions about we have not yet spoken are not time-dependent, or their temporal variation ceases to 0. And then, of course, we expect that also the process will come to some limit. Will approach a time-dependent limit for large times for t going to infinity. Doing this formally, what does that mean? If the u does not depend on time anymore, then of course this term here vanishes. So formally, as a limit problem, we expect then the equations where only this part here is left, or only this part here is left, or writing it together again with this general formulation of the j, we expect this type of equations. Of course, our solution is then not depending on time anymore. So specifically, that would be this equation here. So this will be our working horse. This equation will be our working horse, a little bit more general, but basically this is it. This is the equation we will deal with for a long time. And you see again, our starting point can be rediscovered if we forget about the convection, set c to 0. If we take the k constant, say equals to 1, we are then back to the minus Laplacian of u. And maybe now you see why I prefer to take minus Laplacian of u and not the Laplacian, because I put all the derivatives, I always put all the derivatives to one side. Some people also write these equations not like this, but they write time derivative equals. I prefer to have all the storage and exchange terms on one side, and on the other side maybe the external sources if there are some. And if you do like that, then you get, of course, minus the divergence, minus the Laplacian. Okay. Okay, as we said already, this is the Poisson equation. That will be our most important equation. And of course, one can do this everything a little bit more general. Up to now, things were basically linear. One can, of course, say, okay, there is a nonlinear relationship giving here the quantity in the time derivative. There's a nonlinear relationship giving this vector field here, the convective vector field. There's a nonlinear relationship here now depending on the gradient of u, giving the diffusive part. And more or less, if you can handle the linear case, you can more, at least numerically, not in analytical terms, at least numerically you can also handle these types of nonlinear problems. This is then called, if only the nonlinearity appears here, then we speak of quasi-linear, of semi-linear problems, and if it appears here or here, then we speak of quasi-linear problems. Okay, now one thing is missing, the boundary conditions. We said already this cannot be all what we said, and now we understand also more, hopefully more precisely why something is missing, because what we've described up till now are just a general process. The conservation relation plus the constitutive law, nothing else. If we want to describe a specific situation, a specific experiment, a specific process in nature, then of course we have to specify what is specific for this situation, which then uniquely determines the solution for that. And that is done in this stationary case by the amendment of boundary conditions. And in the time-dependent case, additionally, we have to amend initial conditions. So this is similar to the ordinary differential equations. In the ordinary differential equation, the typical problem you looked at was the initial value problem. You specified the initial data, but in the ordinary differential equation, in this world, no space exists, and therefore no boundary conditions. I would now maybe expect sort of a contradiction from you. Have you ever dealt with boundary value problems for ordinary differential equations? Somebody did this? No? Yeah? Why is this not contradictory to what I said? What does it mean to have a boundary value problem for an ordinary differential equation?
Probably we are solving that equation within that boundary, considering that as a limit.
Yeah, but why? What does it mean?
You have conditions on the boundary. That's it.
Yeah, I know what that is. Actually, I know this in 40 years. That was not my question. You should explain to me why. We're not here only to know what to do, but why to do it. So what is the situation if you, for example, if you look at this equation? So I said with the ODEs, to make it more precise, with the ODEs I said, and also to put it in relation. If I look at ODEs, I said, okay, an ODE, this is a very general thing that can be something like that. Of course, this is a vector here in general, or you can also have some t-dependence here if you want. And you can do a lot of things with that. And if you cannot solve it, you do some numerics on it. And what you need here, you need an initial data. Okay, this is an initial value problem. And that means you have a temporal process, a dynamical process. You have it described to a certain amount of time, and then the underlying mechanisms tell you how this process will go on forever. You have an oven, you put your hand on your oven and say, oh, it's pretty hot. And then you know, in principle, how it is tomorrow. Okay, you can also look, this is initial value problem. But what, for example, if I would look at a problem of this type? That's not really a problem to look at because you can solve it directly. This is now what I called here x. T is now x. I changed the name of the variable for some strange reason. And I look at this problem. Do you recognize? Did I have this problem? Did I have this equation already somewhere here? You saw this equation already today? Yes or no? Yeah, it's a Laplacian. It's a one-dimensional Laplacian. Of course, if I go down to one dimension in my spatial description, if I say that's enough, my spatial variation is only in one variable, and the other variables, of course, they exist, but there's no dynamics of my process. I'm interested in the heat conduction in a wall, and of course, the important thing is from inside to outside, and the wall is very large, extended to the rooftop and to the sides. Maybe I can ignore these effects. Then I can come up with a one-dimensional problem. And then here I see the boundary condition. So this is a boundary value problem. A special boundary value problem, which, so to speak, is contained as a special case in what we are doing here. And now we need these boundary value problem, the boundary values. And there are different kinds of, it's not exhaustive, this list now. These are the boundary values I want to discuss. The most natural boundary condition is to prescribe the total flux in normal direction. What was the total flux? That was this quantity coming from the diffusive part, and this quantity coming from the advective part, convective part. And this is a vector field, and the normal component of this vector field is prescribed by a given function. You can imagine what happens. You have, as a natural condition, you have continuity of flux in normal direction at the boundary. You have some flux coming on, and this is just in normal direction transferred through the wall. Maybe other physics is working outside the domain, and then there are other descriptions than I have here, therefore a given function, but this is what is called a flux boundary condition. It's quite a natural boundary condition. What is equally easy to handle, at least for finite elements, is what is then called a mixed boundary value. Namely, I prescribe a linear combination of this normal component and of the quantity itself. And now we can do something which is mathematically quite convenient to investigate, but at least for this type of problems is a sort of a dubious boundary condition. Namely, let's do the following formal procedure. Let's say the alpha becomes extremely large, this exchange coefficient. What would happen formally with this boundary condition if the alpha, and let's put an alpha also to the other side, that it's not so trivial what comes out. If there would be also an alpha times J2, and the alpha would become very large, what would be, so to speak, the limit you expect for this boundary condition for alpha going to infinity? That means your exchange, there's a sort of exchange described, this exchange becomes faster and faster. Now do it formally. Divide by alpha, and let alpha go to infinity. What happens formally? Pardon? U equals G2 would be the consequence of that formal. Of course, it's only a formal consideration because our solutions we are looking at depend on this alpha. So to do this rigorously, what we need to know that nevertheless we have this dependence, these quantities which are here remain bounded. Because otherwise it will not help us that the 1 over alpha goes to 0 if the other quantity explodes. So that's pure formal what we did. There's no proof whatsoever. But we expect that that would be a reason to have also this other boundary condition, and that is called the so-called Dirichlet boundary condition. Just impose the unknown quantity. There are applications in mechanics where U stands for the displacement, and then, of course, the Dirichlet boundary condition has a meaning on its own. displacement 0 means just I have clamped my whatever. But if I think of temperature, if I think of concentrations, it's quite a strange thing to say I prescribe my concentration, I prescribe my temperature as 0. Even if I do not mean 0, if I do not think in absolute temperature, it's even if it's not U equals to 0 is absolute temperature, it's hard to think how to do that. You have to think it as a limit actually of such a type of boundary condition with a heavy exchange. But in any case, we will investigate all these three types of boundary conditions. So in the general situation, our domain boundary is subdivided in three parts, omega 1, 2, 3, and we have these three types of boundary conditions on these parts. And as I said already, if we also look at the instationary problem, at the time-dependent problem, that means we have our problem only at a domain, but we have the space-time cylinder to look at. So this is the ODE world, and then in the PDE world, so to speak, the dot, where one point where everything lives, now become our domain omega. That would be stationary. Here we have our x, and in the instationary situation, as I said, I'm not going to look at, my drawing facilities are a little bit restricted, but maybe you can imagine what I mean. Hopefully you can imagine what I mean. We have here the omega, and here we have the t, and then we have here xt in the instationary case. But that is something for next semester. Or maybe at the end of the semester I will give sort of an introduction to it. Anyway, so, okay, so that's good. We still have some 18 minutes. And now I come to this promised nice pictures, just to see what that can mean in real applications. With typically totally untypical for this course, what I'm doing now. So we start off, we have several examples. This one is a simple, we start off with this one that's very close to what we are doing, and this is a problem which in the end, I thought in a few weeks, I think in a few weeks we can compute this and also understand this. That is the question about electrostatic potential in vacuum, and what we have is we have here two cylinders with different charges here. And so what are the conditions? So what turns out is there is, again, the Laplace or the Poisson equation comes up. So the Poisson equation appears, so to speak, everywhere. Now for the description of this electrostatic potential, V, the parameter here now is called the permittivity. There's a certain source here. And what do we have? We have at the cylinders, we have plus and minus 1. At the bottom, we have 0. And at the other parts of the boundary, we have gradient. The normal direction is here not written by nu, but by n. Hope you can forgive this. The normal derivative is equal to 0. So this is a boundary, again, let's first look at this boundary condition and give this an additional name. This boundary condition is called the Neumann boundary condition. And we have seen this already because here we have no convective parts, so the flux reduces just to this quantity. So in the situation where we only have diffusion, the flux, what we call the flux boundary condition, reduces to a prescription of the diffusive part in the normal direction. And if the coefficients are constant, it just means to prescribe the derivative in the normal direction. The directional, that's just a directional derivative here. And in this case, we call this a Neumann, and here a homogeneous boundary condition. Maybe another word, if we have equations, and if, say, PDEs are also boundary conditions, on the right-hand side is 0, then we call these equations homogeneous, as you did it already in linear algebra, for example. Okay, this is what comes out. What you see here, this is the color coding of the quantity. You see here flow lines. These spaghettis here are flow lines, and these colors indicate the value which is on there. So that is a typical outcome of such a computation, which hopefully tells you something. But of course, the first question you have to ask yourself, if you get such a nice picture, and the world is full of tons of software which produce you such nice pictures, is this reasonable? Just because it's nice and colorful, does not mean it's reasonable. You have to understand somewhat the numerics to figure out whether this is reasonable or this is rubbish, what you see. And the more colorful and the more nice it is, the more doubtful I am. Okay, so what we will do is we will generalize a little bit what we had already. We said already, okay, this coefficient might depend on x. And if you do this, you write this out, you see now this differential operator becomes a little bit more complicated. You have your matrix times the first order derivatives, and from this, again, the derivatives and the sum of that. It's just explicitly written down what is the divergence, what is A times the gradient. And we discussed already that it's reasonable to assume and also necessary that this matrix is positive definite. More precisely, uniformly positive definite. The positive definiteness cannot get worse and worse if you approach some point in the domain. How do you measure, so to speak, the quality of positive definiteness of a matrix? What does that mean? It's uniformly positive definite. What do you know about positive definite matrices? What is the characterization of a symmetric matrix to be positive definite? Not the one I've written down with the inner product, but what is another one?
Determinant should be greater than 0.
Bitte? Pardon?
Determinant should be greater than 0.
No. Yeah, this is. You think of the two-dimensional case, and then it has something to do with the determinant. But that's only in the two-dimensional case. In the two-dimensional case, you're right when you say the determinant should be greater to 0 and the 1, entry should be greater or equal to 0. The principal minus, how these things are called, the determinants of the principal submatrices should be greater or equal to 0. Crazy stuff with these determinants and so on. Nobody likes that. And therefore, it's a much nicer way to characterize that, independent of the two dimensions. Yeah? The eigenvalue should be positive. So what we require in the uniform case, that all the eigenvalues have a uniform lower positive bound, varying over all points in space. That is meant here with uniformly positive definite. We come to this in more detail. So that is another model. Again, it looks like the Laplacian. This describes stationary groundwater flow in what is called a fractured medium. That means you have a rock, for example, but it has fractures. It has openings of different widths. And of course, you can imagine that in these channels, the larger the channels, the more the flow will go through these larger channels. This is modeled here by this quantity A, which is this fracture width, of course, and this is something because there's not such a thing like that a homogeneous material in nature. In technical application, you can think of homogeneous materials, but in nature, you never have something what is homogeneous. So this is something which is varying in space and time, then gravity turns up, viscosity, and so on. And then there is pressure acting here, and basically this is the pressure coming from the height, and the other is the pressure coming from the gravitational part. We don't have to understand now the equations too detailed, but you see it's basically this again the Poisson equation again with a mixture of Dirichlet and Neumann boundary conditions here. The Dirichlet boundary conditions just mean I fix the height, so to speak, of my water level. And the Neumann boundary condition says this is an impervious part of the boundary. Nothing flows through it. No flow. And that is what comes out. You see here in the colors, what you see here, the height, and you see in the height again is coded in color with the flux, with a measure for the flux. And you see here there are special channels where the flux is particularly strong. Okay, a time-dependent problem. Okay, this we saw already. This is what we called the heat equation or the diffusion equation. We saw already the boundary conditions which are possible. And this is an example now, the motion of energy, so the distribution of heat in a, so this comes from material sciences. You think of a piece of material which is fabricated in a fancy way as you do it nowadays. You take 24 materials and you glue them together in a strange way, and then you get something new which has new properties. Okay, and this is, of course, here for us, this means that it's all reflected in the K. If I take two materials of different K, of different conductivity, glue them together, that means that the one half I have a low K, say, and the other half I have a large K, something like that. Okay, so this is what you see here. We have basically two values here. We have a large value in one part and a small value in a lower part. And that is the only difference. Of course, this again, if you think very carefully, you should now protest. Because you should now say, it doesn't make sense what is written there. If the K is a discontinuous function, then of course the K times gradient of U is also a discontinuous function. What the hell does then divergence of K times gradient of U mean? At the moment, in a naive view of these equations, which we have adopted at the moment, saying, so to speak, what you see is what you get. I write down some derivatives, then these derivatives have to exist as continuous functions, and all these functions have to add up to the equation what is standing there, point-wise. From this, what is called a classical solution, from this point of view, this does not make sense, what is written here. You agree with me? So we have to think about a new notion of solution such that such a simple thing like a laminated material composed of two materials makes sense. One can circumvent this a little bit, speak of transition boundary conditions and things like that, but there is a problem. Okay, and here what do you see the outcome? You see the strong variation in the temperature field to these different materials. And here you see the temperature profile at one instance of time. The problem is here now a little bit how to plot this, because we have, or how to visualize this now, because we have at least two spatial variables, but in addition we have time. So there is too much to visualize already to some extent. So what we did here is we fixed time, we looked at one instance of space, and we fixed time here at this point 1, look at one instance of time and looked at space, and see here, and you see here with the color coding, you see here the temperature, and the arrows, they indicate indicators for the flux field. And here again another representation. And now here it's the other way around. It's this is a misprint here over there. This is now one instance in space. Now is it? In any case, it's a variation in time. I have to admit I don't know what is on this picture. Something strange. Okay, now maybe I close with this. This is one equation which we certainly will not deal with in this course, but maybe a little bit in the next semester. And that's pretty much related to this equation here. Also, it does not look like that. That is what is called the wave equation. So that is now, again, another physical phenomenon, or a phenomenon very much related to convection, namely the evolvement of acoustic or optical waves. And if you write down similar things, you're not dealing with now with energy or with mass as we did till now. You deal with momentum. And dealing with momentum, what is the most simple, the most important law you have to know? Dealing with, we know conservation of momentum, but there's one, if you go to much simpler situation, you will not have called it momentum. At school you have learned about one law, which is related to momentum. Momentum has to do with force. Which law from school has to do with force? Yeah, something with second is not bad. Newton's second law, what does that say? We had it also on a transparency some time ago.
Rate of change of momentum is constant.
Say it again, I haven't understood it.
Rate of change of momentum is equal to
yeah.
force.
Yeah, okay.
Impact.
Okay, and we do it a little bit more simple and relate momentum to what is it? To the height and to the velocity, and then the second derivative at the acceleration, we are then there. That means we have a relation between the second derivative, the acceleration, and the force. So that means we get second time derivatives into play here. And that is the reason why we have here a second time derivative here. So this term basically comes exactly from the law we have just discussed. The quantity, the parameters are gone. They are all scaled to 1 now. So this is basically force equals m times second derivative. That is this part. And this part we know where now we know where Laplacian comes from. This part comes from the spatial exchange here. So this is now the equation which comes out. It looks very, very similar to the heat equation. The only thing is what we did, we exchanged the first derivative by a second derivative. But the behavior of the solutions of this equation is a totally different world. Because also the physics is, of course, a totally different one. It's clear. It has to be something totally different. So that is that's the wave equation. For the wave equation, we now have 2 time derivatives. We need 2 initial data. We need position. Let's say u is the position. So we have u, the position. U prime, first derivative in time is the velocity, second derivative, the acceleration. So we need position and velocity as initial data, and then we can let our wave go. This is what is said here. These 2 initial conditions, boundary conditions, okay, can be similar to what we discussed. And now we take a membrane. That is what is described here. That's the most simple model for a membrane, which also ends up with the Laplacian. Now u is the displacement of this membrane. So that means, what do we have at boundary conditions? U equals 0 now has a physical sense. It just means the membrane is fixed at this part of the boundary. And here, this means no flux. In general, that means the membrane can move here, so to speak. We have a sort of a fancy initial data. And now this means what happens. You see the wave motions, and you see totally different types of behavior of the solution as you've seen in the other cases here. Okay, so we can go on with the examples. Can be more and more complicated. What I'm not going to do now. I had some movies somewhere. I don't know where I have them. Maybe I show you this picture as a final thing. This thing that I can fit in this method. That is a problem which comes from hydrogeology. So you're looking at problems in the underground, and you know in the underground we have very important things like our drinking water. And we have also nasty things in the underground, like, for example, organic contaminants coming from oil spills or whatsoever. And one idea is, at least alone in Bavaria, we have 10,000 such contaminated sites. So we are not able to clean them up technically. We are able, but we are not able to pay for it. So one tempting idea is with organic contaminants is let the nature do the job. Maybe there are bacteria who eat up the contaminants. And that is the background, that is what is described here. I'm not going into the equations now. So what happens here is I have a very simple flow going from top to the bottom. I have some inlet of one of the chemicals, and that is, so to speak, the contaminant. And the question, so if there would be now no further reaction, of course, convection would just take this contaminant and carry it through to the domain, maybe to the next drinking water well. Diffusion would disperse the profiles a little bit. But maybe something is going on which bring the contaminant bloom, now this is called, to an end, to a stop. That would be very good. Then it would be of no harm. Okay, so you see here, that is already a mesh which is prefabricated for this reason. This is this is what's going on with the first type of elements we want to discuss, the so-called linear elements, P1 elements. And you see here, that is, so to speak, the final state. You see here, apparently, this contaminant, which is what is going on here, is a redox reaction. In this redox reactions, contaminant acts as a donor, and the other substance, which is here oxygen, acts as an acceptor. If you know enough chemistry to appreciate this remark, otherwise you forget it. It means it seems to stop. Everything is okay. And this is fairly well discretized here. Nice picture. We go home. Everything is okay. Now we do this with beta elements. And now you see the world has changed. It's not only changed for 5% or so, it's totally different. What now happens is this bloom is going down more or less unchanged all the way down. So the numerics has done something here which disturbed not quantitatively. Of course, we expect that our solutions are not 100% correct. But it has changed the quality of the solution. It gave us the wrong answer. But there's a numerical effect going on which makes the things totally wrong. Okay, we will, of course, finally discuss this effect. Okay, so let us close for today.